Anna, give me like 30 seconds. I'll grab some water.
Okay. Live stream.
I'm back.
Okay. So welcome everyone to today's seminar. Today we have Dr. Zhen, who is originally from Beijing, China. So he obtained his bachelor's degree at the Peking University in exoplanets. And in 2018, he finished his PhD at the Kavli Institute for Astronomy and Astrophysics on the topic of young stellar objects. Later, he joined the VVV survey at the University of Hertfordshire, working with Professor Phil Lucas. In 2022, he moved to the Universidad de Valparaíso in Chile as an independent research fellow. And he's now an assistant professor there and also a member of the Millennium Institute of Astrophysics. Thank you so much, Zhen, for accepting our invitation. You may start when you're ready.
Yeah, thank you so much for inviting me, Anna. And today I will talk about eruptive young stellar objects from the large-scale survey era. I hope you can see my slide, or are you looking at myself?
We're looking at you. I don't know what I do.
Okay.
There you go.
Okay. Now you can see my slide.
Okay, sorry.
Okay, perfect. But let me know if there is some problem, because I had these issues before with my laptop. Okay, so as Anna introduced, I am currently a faculty in Universidad de Valparaíso in Chile, and today we are going to talk about eruptive young stellar objects from the large-scale survey era. Most of this work has been done in the collaboration of the VVV and the VVVX surveys, also with my colleagues around the world. Are you looking at? Okay. Can you see the slide changing? Okay, yes. Perfect. And this is the outline of the talk. At the beginning, I will give a brief introduction about mass accretion on young stellar objects. And then we focus on one type of the outburst on young stars called the FUor-type outburst. Later, I will give a brief introduction about the VV survey team and what we have been doing in the past few years, and then some ongoing works, including several individual targets. In the end is the introduction about our future work and about our research team. So we know that mass accretion is actually a universal process in astronomy, because the mass accretion disk exists along all the different types of astronomy bodies, including the active galactic nuclei in the center of the galaxies, around binaries, and around young stellar objects, and even around young planet. And one typical phenomenon around this mass accretion disk is that the mass accretion itself is unstable. So here, I'm going to give you a brief introduction about the pre-main sequence evolution of young stars, because I know that most of you are not doing star formation. So the overall timescales of a pre-main sequence stage evolution of a solar mass star is about 10 million years. At the beginning, at the 0.5 million years of age, we call these stars protostars. And they are class 0 and class 1 according to their spectral energy distribution. Later, we call them T Tauri stars and class 2 or class 3 based on their shape of the SED. And then we can see here from the SED that actually those class 0 and class 1 type of protostars, they cannot be observed within the visible light. And then class 2 and class 3 stars, we can see their photospheric emission from the optical wavelengths. And then we can also see the contribution from a circumstellar disk. And today we're going to talk about some variable young stars during the class 1 and the class 2 stage with the age around 1 million years of old. And then all of these stars, they have ongoing planet formation. On the right-hand side, you can see a ALMA detection of a protoplanetary disk around a 0.5 million years old target. We can already see some rings and gaps here that's suggesting that there are already some planets forming in this stage. So on the left, you can see an artist impression of the protoplanetary disk. You'll see a central young star here, and then some rings and gaps opened by the accreting young planet. And if we are looking at the innermost of the disk around this star, what we're looking here is that the material from the disk is accreted onto the star. And this usually on the classical T Tauri stars, this scenario is controlled by the stellar magnetic field. And this is common among low mass young stellar objects. So the disk material is truncated here and then accreted onto the star and form this accretion shock, which is really hot. So we can observe them from the UV emission and also some narrow line emissions from the metal lines. And then this info accretion flow will also be observed by especially the hydrogen recombination lines like H alpha in the optical, and also pattern series and Belker series in the near infrared. Due to the balance of the angular momentum, we can also see some disk wind and jet launching from this system. So now we're looking at a relatively stable system. However, as we know that this accretion is not actually really stable. So on the left, there is a summary work by Lynn Hillenbrand, and she published this chart to demonstrate the different types of variabilities on young stars. We categorize them with different colors. So the blue color here representing the variability related to the mass accretion event, and then the red is relative to extinction, and then the green is for binary disks. So if we only focus on the blue color, we can see there is a general trend that with longer duration of the event, we have higher optical amplitude here. And in general, there are two types of variability related to accretion. If you look at the left and lower amplitude side, we have some short duration and low amplitude variability. We call them routine variabilities on young stars because we always observe this kind of variability on young stars on timescales of several days or several weeks. On the other hand, we have FUor-type outburst, we have V1647 Ori-type outburst or EX-loopy-type outburst. Those are the high amplitude variabilities we observed on young stars, and they are not really frequently detected on young stars. So we call them outburst, which is relatively to the enhancement of the accretion rate of this object. On the right-hand side, there is an example from the Gaia Science Alert. You can see this is a light curve. So it is time versus the magnitude of the star. And then we have routine variabilities with low amplitude, and it happens all the time. And then we have an outburst with about 2.5 magnitude, but lasts for a short duration. We call them the EX-ORA type outburst. So why we want to study accretion burst on young stars? We have three reasons. First of all, we want to understand the stellar mass assembly. So how much mass was accreted onto the star during this outburst, and how of this outburst contribute to the overall stellar mass in the end. We also want to understand whether there are star, disk, and planet interactions at the innermost of the disk, because at the standard scenario here, we didn't include a giant planet. What if we have a giant planet near the star, and how the giant planet affect the mass accretion of the star, and how the accretion burst eventually feed back to the planet formation? In the end, we also want to study the physical mechanisms that create this outburst, whether a typical accretion disk can create this event, or we need some extra source that created this outburst. For example, this is Antonis Alice observed this using ALMA, that one outbursting star has an accreting stream that linked from the outer disk to the inner disk and create this outburst, perhaps. So today, we're going to focus on one type of the outburst called the FUor-type of outburst. And I assume that everyone can recognize this constellation is one of the most famous constellation here is the Orion. And Orion also contains one of the largest and closest star-forming regions to our solar system. And you can see the Orion Nebula here, and also the pretty M42 here. And then if we go to the head of the Orion, on the right-hand side, so between the head, if you can see my mouse here, between the head and then the Postman sequence star Betelgeuse, in the center, there's a region, there's actually a small cloud here. And if we zoom in to this cloud, which is called Barnard 35, if we zoom into this cloud, you see that there's a bright and yellowish color star here, embedded here in the inside the cloud. So this is actually the star called FUor-Orionis. It is here. If we zoom in here, it is actually a binary system with two stars, FUor-N and FUor South. And actually, about 80 years ago, so people has observed that this star went into eruption. As early as 1930s, we see that there is a 6 magnitude outburst on this FUor-type star. And then the star remained on the photometric maximum for about 80 years until nowadays is still relatively bright. So this became one of the prototypes of the outburst on young stellar objects. So after that, people discovered several other eruptive events on young stars, and they start to conclude that this kind of long-lasting outburst on young stars with large amplitude called FUor-type outburst, named after FUor-Orionis. Although you can see that even among these 3 FUoris people discovered in last century, that these 3 objects also have some difference in their light curve. So FUor itself has a fast rising outburst and then stay on the photometric plateau for almost 1 century. And this one, V1015-7 SIG, had an outburst, but after the outburst, we see a decay, which is not observed on FUor itself. In the recent years, with the help of several satellites, including Gaia and NEOWISE, were able to maintain the high cadence light curves of this object. And then one of the Gaia outbursting YSO we discovered is Gaia 17 BPI. And this object, we detected outbursting Gaia, which is shown in the blue lines. However, when Lynn Hillenbrand went to check the NEOWISE light curve, which is in the mid-infrared, we're able to see that there is a pre-outburst even before they noticed the Gaia outburst. And this pre-outburst was 2 years before the optical outburst, suggesting that there's something happening in the circumstellar disk that eventually triggered this outburst. So the outburst started from the disk instead of starting from the star. After analysis, the number of the objects that we detected have this outburst on young stars, we're able to have an overall conclusion about the time scale of this event. So it's about one outburst per 10,000 years on one star, and after that, they have decade-long decay that the star remain bright after the outburst. So here I'm showing you the spectral energy distribution of a normal young accreting star. What you are looking at here is two components. The first component is the photosphere, shown by the green here is coming from the star. And then we have an accretion disk coming from the pink color lines here. So you can see there are two components, a photosphere and the accretion disk. However, during the outburst, the star has completely changed. When we took a spectrum of the star, we figured out that they look completely strange because we're looking at a really bright object, but also when we check the temperature of the spectrum, it looks really cool. It resembles the M dwarfs or brown dwarfs. We see a lot of absorption features in their infrared spectrum. So what are we actually looking at here? We are not looking at the star anymore. We're looking at a bright inner accretion disk. So here, there are three components from the ICD. We have a central star, we have accretion disk, and we also have a viscously heated inner disk here. And this is shown by the orange color. And because this disk has a warm color, has a warm temperature, so when we do the observation, we see a brown dwarf, M dwarf-like spectrum here. Although, even though it is warm, but it covers a large area. In this case, that it has a much brighter luminosity compared to the star itself. So it started to dominate the SED of this system. So the overall SED will look like an absorption object. So here is the definition of FUor-type object on young stars. We find a young star, we see an outburst, and then we see a cool spectrum from the disk. So what kind of mechanism can trigger those outbursts on young stars? So far, there are three main solutions. First of all, it's caused by the gravitational instability inside the disk, and the disk has fragmented into several small pieces, and one of the small pieces accreted onto the star. In the second scenario, we need a secondary object which create the gravitational instability that to the star and to the disk. But this second component is not originally from the system. It's a flyby of a secondary star. And in the end is the thermal instability inside the disk that we do not request any stars or planets to trigger those outbursts. As an observer, my job is actually to find more of these eruptive YSOs that we can feed it to the theoretical astronomers to tell us what is actually going on inside their accretion disk. But as I said, those eruptive behaviors are extremely rare to be detected on young stars, about 10 to the minus 4 per star per year. So to detect more of this event, we need to increase the number of the parent sample we have. So we need to use large-scale surveys. We're also looking for a long duration survey which can help us to capture the full event of the outburst. We also want to observe the stars in the near infrared or mid infrared, which give us earlier evolutionary stage of the stars, which has more unstable accretion disk. So far, there are three surveys which are extremely useful to find this outburst, including the Gaia satellite with Gaia Science Alert, which provides us about 5 eruptive YSOs per year. And the decade-long VVV survey observed the target in the near infrared, and then the NEOWISE survey observation in the mid infrared. Here is an ICD of an outbursting star I observed. which you can see the dramatic change from the pre-outbursting SED to the outbursting SED. And then these three surveys can help us to capture the outburst in different wavelengths. So the VVV survey is an acronym of the VISTA variables in the Via Lactea survey. It was conducted on the ESO VISTA telescope in Paranal Observatory. The initial VVV survey lasted for 5 years from 2010 to 2015. We are targeting the galactic bulge and part of the inner galactic disk region. Most of the observation was done in the near-infrared K-band around 2.2 micron. We have about 10 visits per year. In total, we have about 70 visits for each star in the field. And after 2015, we have an VVV extended survey, which covered from 2016 to 2023. In total, we have about 10 to the 7 variable sources, including 100,000 young-cell objects. As I told you that, the VVV survey covered about 10 years of the photometric baselines, and we also have 100,000 young stars, so give us a great opportunity to search for eruptive young-cell objects from the VVV data. Our young-cell object team in the VVV survey has been working on searching for these eruptive white-cells. Indeed, we found about a few hundreds of eruptive white-cells in the VVV data. Most of this work has been led by Professor Phil Lucas from Hertfordshire, and also Carlos Contreras-Pina, who is currently in Korea, and myself. So there are 3 steps or 4 steps of our works. First step, we are doing building photometric catalogs based on the VVV time series data. And then we make spectroscopy follow-up observations to do spectroscopy confirmation that we are actually looking at young stars, and then we identify their accretion behaviors using their spectra data. And then the third step is to study individual variable stars, including the stars with high amplitude or with periodic behavior. In the end, Carlos did a statistical analysis which just published this year. He found that around 1.5% of the protostars had eruptive event in the decade of the VVV survey. And here I'm going to show you some of the spectroscopy data we took on those eruptive stars. So here on the right-hand side, you can see the XSHOOTER spectra we took from the VLT telescope. And all of this spectra looks very similar to each other. What we're looking here is water absorption in the H band, look like a triangle shape. And then in the K band, longer than 2.2 micron, we have this deep seal absorption features telling us we're looking at a disk instead of the star. On the left-hand side, you can see the infrared K-band time series from the VVV survey. Most of these FUor-type objects show similar light curves that we're seeing a fast rising timescale here, which is marked by the green colors. However, you do see some diversity here. Some of the FUors, as what we predicted from the classical scenarios, that they stay on the relatively bright plateau for 1 decade at least. Although another few FUor-type objects start to fade quickly. As we can see here, the L22215, and also the one in the corner here that they faded rather quickly after the outburst, indicating that we might be looking at different formation scenarios, formation mechanisms among those objects. We also applied the NEOWISE light curve data of this event, and we are able to make a conclusion that FUors have relatively higher mid-infrared amplitude compared to other type of outbursts we see on those young stars. And also, when we're looking at the timescales here, we are able to see that most of the FUors have fast rising timescales that they reach their photometric maximum less than 2 years. However, we do see some mixtures. Even like some FUors have a more than 3 years long rising timescale, suggesting that they may come from different formation mechanisms. Another object we highlighted here in a monthly notice letter is the case of L22278. It's one of the highest amplitude outbursts we've ever detected on the low mass young stellar objects. And the outburst of this star was captured by Gaia, VVV, and the NEOWISE satellite. And you can see here, the Gaia light curve was marked with the orange color. And the overall amplitude of this event in Gaia is more than 7 magnitude. And then after the initial outburst, if we only look at the Gaia data here, both Gaia and the Gaia B band and R band start to decay. According to the color variation here, we are able to confirm that this decay is actually caused by the changing of the line of sight extinction, which also explains that whether if we look at in the mid-infrared or the near-infrared, we didn't see this decay because they are less sensitive to the extinction event. We also fit some analytical functions to the rising light curves on the right-hand side. You can see here is the 3 different facilities from WISE, VVV, and Gaia. They have 3 different rising curves. And we can see there is about 100 to 200 days delay between the Gaia optical rising light curve versus the WISE W2 band mid-infrared rising light curve, suggesting that, again, this instability is originated from the disk, not directly from the star. The inner disk start to get hotter first and then create outburst onto the star. At the moment, in collaboration with theoretical astronomers in Leicester University, we are working on some theoretical solutions for this event. And one of the solutions could be called extreme evaporation scenario, that this outburst was created by a giant planet. And then we can have this kind of simulated light curves that match our observation. On the other hand, we are still working on some more traditional methods that can create this outburst, not including a planet. So it is called the thermal instability outburst that we are simulating here in collaboration with Sergei Nayakshin. Another object we want to highlight here is called VVV WIT13. So WIT actually means what is this? Because we are not 100% sure what we're looking at here, or we're not 100% sure what is the mechanism that creates this variability. It is an infrared outbursting source. You can see the color map here is from the Spitzer mid-infrared map, and this target is located within a star-forming region, and all the pink little dots indicating the actually the currently known young star objects in this field. So these hundreds of young stars form a moving cluster of young star objects. And then when we zoom in to this target, and we can see that, you know, there is a galactic dark cloud in front of this star. So unfortunately, we cannot see any visible optical data from this star because it is blocked by this dark cloud. And this star is located behind the cloud. Although if we look at the WISE data, the WISE image from 2027 to 2020, we see a massive outburst here. So now I'm showing you the time series light curve of this object. On the left-hand side, we captured the outburst in K, W1, and W2 band from VVV and from WISE satellite. And from the K band data, we can see that there is possibly, I'm not 100% sure, but there's possibly a periodic variability before the outburst, and then the star went to outburst with about 4 magnitude. And then after that, it started to decay about 2,000 days later. In the WISE wavelengths, we also see this outburst in W1 band and W2 band. When we took the spectrum of this object using VLT XSHOOTER, we can see an outstanding CO absorption features during the outburst, suggesting we are looking at a relatively cool but bright accretion disk. However, we also found some interesting features in the H-band spectrum around 1.7 micron. We've been asking the young star object community what is actually going on here, but then none of our star formation people can recognize these absorption features until we start to ask somebody who working on planet science and working on red nova. Actually, my colleagues from UCL, Sergei Yurochenko, and also my colleague from Poland, Kamiński, they recognize that this is actually the aluminum oxide absorption features, which is commonly seen around red nova. If you are old enough, like myself, you can remember that in 2009 or 2008, we had a really nice red nova event called V838 MON, and with a pretty image taken by HST, by the Hubble telescope. So in this source, we detected aluminum oxide. However, we also find these aluminum oxide absorptions around young stars, which is one of the first young stars we ever seen this aluminum oxide absorption bands. We can actually fit this absorption band really well compared to our theoretical models with a temperature of only 600 Kelvin. After a few years, this kind of aluminum oxide band just disappeared, and then we can only call it a temporary structure. And also you can see compare different epochs of the spectrum, and the CO become fainter and fainter here. And we also see some molecular hydrogen emission indicating an outflow here. So how do we explain this event? We are building a theoretical team here, including Professor Sergei Nayakshin, Matthias Montesinos, and Vardan Elbakian. So our theoretical solution is actually, we are looking at a tidal disruption of a gravitational instability form, the planet core at 123 AU. So what we're looking at here that, this 3 AU is estimated from the period of the pre-outburst, around 1700 days. If you do a quick calculation, assuming a solar mass star and then the Keplerian period, and then the radius is about 3 AU. And then we're also able to explain why in the W1 band, we have a larger amplitude compared to the K band. It's actually the peak temperature of this scenario is about 800 Kelvin. So it can explain why in the W1 band, it is more higher amplitude here. We can also understand why there is an intermediate duration of the outburst and not like FUor-type, it keeps brightening for several decades, but this object only have a brightening stage about 2000 days, which is equivalent to the dynamical timescale of the radius. And then we can also detect some cool molecular absorption features because we're looking at a hot inner ring instead of a hot inner disk that directly linked to the star. So here is a simulation made by Matthias Montesinos earlier this week. And this is a simulation about how a gas giant planet got tidally disrupted by the central star at the former ring structure at 1 AU. So now in the next few minutes, I'm going to talk about some short duration outburst, which discovered by Gaia. So this kind of outburst has a common feature that they are repeating. So by taking care of individual outbursts, we can understand how this kind of a small scale outburst is happening on young stars and why they are repeating. And this work has been done in a collaboration with Mike Kuhn from University of Hertfordshire. We found a Gaia outburst here from the Gaia alert. And then actually this outburst was originally discovered by VVV in 2014. And then after about 10 years from the Gaia science alert, we see that this outburst is ongoing again. And then we download the data from the Atlas small telescope, and then we can still see an outburst ongoing until a few weeks ago. So this year, we took a lot of spectroscopy observations using Chilean-based telescopes. We're able to see this so many emission lines here in the K band and H band spectrum. And then we are also able to see the change of the line profiles in the near infrared with several epochs we took earlier this year. Another similar object we also detected from Gaia Science Alert is Gaia 24CCY. We also see this, routine variability and outbursting variability on this target. And earlier this year, when we received alert from Gaia, we started to have spectroscopic follow-up observations using VLT XSHOOTER and also using several telescopes, including SOAR and SOT in South Africa, and then HCT from India. And from here, we compare the quiescent spectrum versus the outbursting spectrum, and we can see the dramatic change on the pattern and gamma line here, and also the helium-1 line here. And this work is led by a PhD student, Koshavendra from Tata Institute in India. Another work we recently submitted is leading by Dr. Colin Morris from Hertfordshire by analysis the mid-infrared variability from the NEOWISE catalog. And then we are not searching for the entire sky. What we're doing is we focus on one star forming region, thickness X, and then we check the mid-infrared variability of a few thousand of stars in their star forming region. And we were able to see 17 eruptive young stellar object candidates from this region. And then you can see their light curves here show really similar light curve to the FUor-type, that you have a quiescent stage and then the rapid outburst and then stay on the photometric brightness platform after that. From a statistical point of view, he also finds that actually younger system with a heavier accretion disk usually have larger variation amplitude compared to the more evolved system, which also consistent with our scenario that actually the accretion burst caused by some instabilities inside the accretion disk. So in the next few years, we will enter the Rubin era, which is an era of variable stars, a era of time domain astronomy. And we need to use machine learning to help us to understand the data from the Rubin telescope. And actually, a few months ago, we had this chance to become the first public visitors to the Rubin telescope. And then here in the following the yellow arrow here is actually the Rubin telescope, and then here is a zoom-in view of Rubin. And right now I'm participating in a machine learning program called ALERCI, which is the official Chilean broker to automatically identify variabilities of variable stars or extragalactic sources identified from the Rubin data. And then one of them is to study the young stellar objects. Here I show you one of the examples from the ALERCI team that we recognize a young stellar object has an outburst, and then it looks like an FUor-type outburst from the ZTF telescope data. So in the rest 5 minutes, I'm going to talk about our challenge and future works and introducing our research team. So as we know that the VV survey has finished, right? So VV light curve in the past. We had a near-infrared light curve from 2010 to 2019, but however, whatever we do now is in the past. So we need new photometric data. So photometric revisits are very important in this field, especially at the moment, there is no ongoing near-infrared survey data until the Roman telescope, which will be launched in 2027. So we have a few years of gap here. So this year, we started a new survey called the VVV Renew survey, which using the Blanco telescope in Chile. We are going to revisit the central galactic regions here marked by the orange color, which also been covered by the VVV and the VVX survey. So we're trying to revisit these regions and to provide more photometric data to these systems. And then we also want to get more spectroscopy survey data, which we are ongoing to bid some large-scale surveys from ESO. And then in the end, our final project is to study stellar mass accretion among protostars, because we know that currently we have a good sample of spectroscopic data of classical T Tauri stars that we can observe them in optical. But for protostars, we have to observe them in the near infrared. So a large group of these protostars, we can understand the mass accretion rate among the protostars and how would the mass accretion evolve from protostars to the T Tauri stars. So here is our research team, the team of Protoplanetary Nursery. It's a China-Chile joint research project. We have two main scientific goals. We want to study spectroscopy confirmation of the eruptive and embedded young stellar objects. We also want to study the star and the planet interaction at the youngest evolution stage, including the gravitational instability and also their impact to the accretion rate of the star, and also study the obliquity of the young planet. Here I show you the teams in Chile, led by myself, and also in China, leading by Professor Xuesong Wang from Tsinghua University. Okay, I will summarize my talk here. So my take-home message, first, large-scale photometric surveys are powerful tools to find those eruptive young stellar objects. So far, we have been spectroscopically confirmed 50 eruptive young stellar objects. Around 20 of them have FUor-type spectrum. And then we also see a lot of diversity on the light curve morphology, indicating that we might have different triggering mechanisms of these events. Rapid follow-up observations using Chilean-based telescopes is actually our ongoing work. We are working on the Magellan telescopes and SOAR telescopes to get more spectroscopic data. And our next step is to study eruptive young stellar objects and their correlation with the planet formation. I also want to invite you, if you have the chance, to visit our beautiful city, Valparaíso, and to discover more collaborations and topics together. Thank you very much.
Thank you. We have questions? Thaisa and Rogério? First, go ahead, Thaisa.
Hi, thanks very much. Thank you very much for your presentation. Very interesting. And I have a question, like, I find similarities between this accretion disk and young stellar objects to accretion disks in AGN. And and also you said that the flares that you are seeing, you interpret mostly as due to the flares in the disk, not in the star, right?
Yes.
So I'd like to know if you have something to comment about this. So I wonder also if these flares would be a means to clean the disk, to leave the planets orbiting the star without interplanetary material. So many questions.
That's a very good question, actually. We discussed about this before, that even the timescales of AGNs and this accretion bursts on young stars, they are very similar to each other because of the physical scale of a supermassive black hole and the young star is basically the same. The difference is the mass, isn't it? So actually, some other works using the GWST data, they found out that after the outburst, there is some evolution of the chemical component inside the disk. So because after the outburst, the temperature of the disk will dramatically change to 1000 Kelvin. So in this case, it will melt a lot of the ice that already formed inside the circumstellar disk, and then give these molecules another chance to mix and then to recombine. So it actually helps to build complex organic molecules around those circumstellar disks. And also, they have impact on the formation of comet. So there are a lot of applications of these events.
Interesting. Thank you.
Rogério?
So thank you for your talk. Very nice. I may have lost a bit of it, but my question is related to the near infrared spectrum you were showing. For me, they are quite similar to red giant stars. Okay, so I may have lost something. Why the CO in absorption in the case of the objects you are studying is from the disk and not from the star? And why are you not detecting the 1.6 micron CO absorption bands? And in those spectra, if it is from the disk, it would be hot dust. I would expect it to be higher in the redder part of the spectrum than in the bluer part?
Yes, that's a very good question. I apologize, I didn't have time to explain the details of the accretion disk here. So actually, as you said, we're looking at a cool spectrum, and then they are very similar to red giant stars. I need to accept that. And the way we distinguish of these young stars and the red giant stars is to looking at if they have 13 CO absorptions. And the 13 CO absorptions, because the 13 CO only created from the nuclear reaction inside the star when the star getting older. So the young star is supposed to not have any 13 CO. So we will zoom in to check this around the 2.35 or somewhere. There's a 13 CO absorption band, which is commonly seen around red giant stars. So this is how we distinguish between FUors and red giants. And on the other hand, most of the red giant stars don't have the water absorption. So that's also one way to help us to distinguish it. And the reason that why this one looks bluer here, because I actually manually changed the estimation of the extinction of this event. So we actually use this triangular shape in the H-band to estimate the extinction, because we assume they all look the same with accretion disk. That's why they all look like that, because I removed all the extinction.
So one following up question here, like the water feature, you see it also in TPHB stars, okay? So it's not completely clear to me, so the way to distinguish besides one very specific CO absorption method.
Yeah, because there is no 13 CO, so we think these are young stars.
Okay.
Yeah, because we also collected a sample of AGB stars based on their light curve features, and then we zoom in to check that actually they have some difference in especially around 2.3 micron wavelengths. But you have to really zoom in to see the difference.
But it's quite incredible that they look very similar.
Very similar.
They're very similar. But AGB stars don't really have the outburst. They have the dipping event, not the outburst.
Yeah.
Do we have more questions? I think Horacio. You're muted.
You're muted, Horacio.
Hello?
Hello, go ahead.
Okay.
Mais alto, Horácio.
Thank you very much for your talk.
Horácio, mais alto.
Alô?
Tá muito baixo.
Alô?
Fala mais perto.
Oh, alô? Tô em cima do telefone. Alô?
Tá bem baixinho. A gente não consegue te ouvir.
Tá.
Ok, go ahead.
Tá, vamos deixar. Okay.
No, eu acho. Do you hear, Jen?
I can hear very low. Yeah, we can try.
Let's try. You can type it up in the chat.
I wonder if you forgot longer wavelength observation for WIT13.
So longer wavelength observations for WIT13, is that right?
Yes.
Yes, that is a very good question. Actually, we are thinking about it. Maybe we want an ALMA observation of this event, because currently we couldn't find any longer wavelengths right now, but then ALMA would help us to identify the mass of the disk for sure.
Thank you.
Anything else, Horácio?
Okay, I heard you. Thank you.
Good. Any more questions from Zoom or YouTube? No?
I have one.
Go ahead.
Hi, look, can you hear me?
Yes, go ahead.
So thanks for this highly illuminating talk. I have one very stupid question, I guess. We know that YCOs, they overall probe the galactic structure, but is there any expectation that the type of the light curve may correlate with the environment? Do you expect to see some bias in the class of the light curve with the environment, maybe focusing specific type? Because I was wondering if maybe some local turbulence, I don't know, might affect the intrinsic mechanism. Is there any expectation about this?
So far, we don't. Actually, you propose a good question, which is we are planning to study in the future is to do more statistical analysis, not only looking at the high amplitude event, but also looking at the smaller amplitude and shorter duration event from Rubin or from ZTF, because it gives us a large sample around different star formation regions with a different environmental effect for sure. So with this, we are trying to see if there is something we can see. But then for the FUors, I think they are distant and they are large amplitude events. So we think maybe they don't have a really strong connection with the environment. But the smaller scale outbursts, we believe they might have some relationships. So we are trying to see this in the future.
Okay. More questions? Do we have questions from the Google Doc? Let me check. No. So I have a naive question. Can you explain more what NEOWISE is?
NEOWISE is a satellite. So it's the extension of the WISE satellite. So the WISE satellite took several years of the mid-infrared observation, but after that it ran out of the cooling gas, so it started to shut down. But then I remember around 2015, and then they started to restart this satellite, they reactivate it, and then now they can only observe in the W1 and W2 band around 3.4 to 4.5 micron. And unfortunately, earlier this year, NEOWISE finished the project. Now there is no mid-infrared survey anymore until the future Roman telescope or other telescopes launching.
Okay, and what about Euclid? Euclid is not useful because it's just near infrared.
Yeah, but Euclid is not doing the variability, right?
Yes.
Yes, so that's also one problem. You might have one or two data points, but then it's not like repeatedly observing. But yes, Euclid will also be very useful.
Okay, if we don't have any more questions, let's thank you again.
Thank you so much, everyone. I'm really looking forward to visit you in person.
Yes, soon. We have an airport from Monday.
Oh,
Airport will be
perfect.
back.
Yes,
Bye-bye.
because geographically we are not far away.
Yes, exactly.
Thank you.
Okay, thank you, guys. See you. Bye-bye.
Bye.
Ele é muito
Ele é japonês, né?
Chinês.
Chinês.
chinês. A gente viu ele a última vez no
Lá
flood.
Hã?
No flood de La Serena. Porque teve um flood.
Ah,
né?
lá
Quando
na
aconteceu.
reunião da LSC.
É, e daí a gente